wave so massive it swallows Mount Everest. Hollywood called it the ultimate disaster, but physics tells a completely different story.
The 2009 blockbuster 2012 depicted global extinction in mere hours. But could a mega flood of this magnitude actually happen?
The film relies on Charles Hapgood's theory of Earth crust displacement, claiming entire continents can shift thousands of miles overnight. In reality, Earth's tectonic plates move at just 1 to 10 centimeters per year. Shifting continents in hours defies physical resistance. The film blames mutated solar neutrinos heating the Earth's core like a microwave. But subatomic physics tells us otherwise. Trillions of neutrinos pass through your body and the Earth every second, completely inert, interacting too weakly to generate heat.
If core temperatures actually reached 2,500 degrees, catastrophic global volcanic eruptions would begin years before any sudden crust shift.
Real ocean dynamics work differently. In deep open water, tsunami waves have immense energy, but measure less than 3 feet tall. Only when reaching shallow coastal shelves does friction slow the wave, forcing its vast kinetic energy to surge upwards into a megatsunami. The climax depicts secret high-tech Arks in Tibet, engineered to survive catastrophic ocean impacts and save selected populations. Engineering vessels to withstand thousands of tons of dynamic wave pressure, while enclosed in mountain valleys, presents extreme physics hurdles.
While global floods remain Hollywood fiction, real megatsunamis do exist. In 1958, a landslide in Lituya Bay triggered a record 524-meter wave.
Submarine megaslides and volcanic caldera collapses pose true planetary risks, capable of devastating coastlines without violating the laws of physics.
Hollywood creates masterworks of theatrical terror, but reality is governed by precise physics. The Great Flood remains purely cinematic magic.
Computer simulations show what happens when billions of cubic meters of water displace simultaneously across major landmasses.
Metropolitan cities submerged under hundreds of feet of ocean water, an iconic image that defined modern disaster cinema.
Director Roland Emmerich spent over $200 million to ground these catastrophic scenes in visual realism.
To reach the high peaks of Tibet, an ocean wave would need to rise over 1,500 meters above normal global sea levels. Physicists and geologists quickly realized that the energy required to lift that much water violates basic fluid dynamics.
So what would it actually take to create a real-life Great Flood? And where did Hollywood's script get the physics completely wrong?
To understand the truth, we first have to examine the catastrophic scientific trigger that started the apocalyptic chain reaction. We unveil the world's greatest mysteries.
The core mechanism of 2012 relies on Earth crust displacement, a hypothesis suggesting the planet's entire outer shell can slip. Popularized by Charles Hapgood in the mid-20th century, the theory proposed that massive polar ice buildup could imbalance the crust. In Hollywood's vision, this imbalance causes continents to shift thousands of kilometers over mere hours, tearing cities apart. Modern satellite geodesy tells a very different story. Global GPS networks track real tectonic plate movement at millimeters per year.
If a continent moved thousands of miles in hours, frictional heat alone would melt the crust, destroying landmasses long before floodwaters arrived.
With crustal displacement debunked by geophysics, the film turned to an even wilder scientific premise to justify its global catastrophe. The movie claims a massive solar flare unleashed mutated neutrinos, penetrating Earth's core like a cosmic microwave oven.
In particle physics, neutrinos are phantom particles with virtually zero mass, passing through matter without leaving a trace.
To heat the Earth's molten core by thousands of degrees,
fundamental physical laws would have to completely collapse.
Real subterranean particle detectors were trillions of solar neutrinos passing straight through the Earth every single second. If mantle temperatures increased, thermodynamic expansion would cause widespread volcanic eruptions years before any crustal slip.
Seismologists monitor core heat and mantle convection daily, finding no evidence of sudden subatomic thermal spikes.
The solar particle threat makes for spectacular cinema, but defies every law of modern subatomic particle physics. Moving from particle physics to fluid mechanics, the cinematic depiction of a towering open-ocean megatsunami presents another physical impossibility. In deep water, tsunamis are not towering walls of water. They are long energy pulses traveling at jetliner speeds.
A wave in 4,000-meter deep water might measure less than 1 meter tall at the surface, invisible to passing ships.
As the kinetic energy reaches shallow coastal shelves, shoaling compresses the wave, forcing it to rise rapidly in height. To crest Mount Everest at 8,800 meters, an ocean wave would require more kinetic energy than Earth's oceans hold.
Displacing entire oceans over continents would require sudden kinetic energy sources far exceeding known tectonic energy storage.
Even asteroid impacts in deep water generate localized megawaves that rapidly dissipate kinetic energy across open ocean distances. Fluid mechanics proves that towering ocean walls, cresting inland mountain ranges, remain dramatic cinematic fiction rather than planetary reality. In the film's climax, world governments secretly build massive, high-tech arks inside subterranean Himalayan mountain chambers.
Designing a hull capable of withstanding ocean impact forces while enclosed in rock valleys presents staggering engineering hurdles.
Hydrostatic pressure from a 1,500-meter wave would crush conventional steel structures instantly upon impact. Constructing 4 massive arcs in secret would require millions of tons of steel and decades of global industrial output.
Beyond engineering, the film touches on a profound human dilemma: deciding who gets a ticket when extinction arrives.
Real-world continuity of government plans rely on subterranean mountain bunkers rather than mobile naval arcs. Naval engineers design deep-sea submersibles for extreme hydrostatic pressure, but scaling them to city sizes remains impossible.
While movie arcs make for compelling human drama, humanity's true survival depends on monitoring real geological threats.
While movie-style global floods are fiction, localized megatsunamis are terrifyingly real. In 1958, triggered a wave over 500 meters high. The force of the water stripped trees and soil off mountain slopes up to 1,700 feet high, leaving a permanent geological scar visible today.
The largest potential wave triggers come from submarine landslides, massive collapses of unstable sediment along underwater continental slopes.
8,000 years ago, the Storegga Slide off Norway displaced thousands of cubic kilometers of sediment, flooding prehistoric coastal Europe.
Volcanic caldera collapses, such as Krakatoa in 1883, generate explosive wave energy that radiates across entire ocean basins.
Today, global ocean monitoring networks like the DART buoy system track deep-sea pressure shifts in real time to provide early warnings.
Radar altimetry satellites continuously measure sea surface elevation within millimeters, catching tsunami energy pulses long before coastlines are threatened. Real planetary risks are governed by energy conservation, giving humanity the science and tools needed to predict, understand, and survive them.
Roland Emmerich's 2012 remains a masterpiece of cinematic disaster spectacle, but its core mechanics belong entirely to science fiction.
Earth's true geological story is governed by laws
that prevent sudden continent-swallowing floods, proving reality is far more stable than cinema. Subscribe to join the journey. Leave a like and share your thoughts below.